Right, good evening everybody. This is part of the DCHNNP Roadshow where we're going to bore you sick with tiddly bits. Chris gave you the intro to SATCOMs back along, talked about orbits. I was involved with commercial satellites for 17 years, so I'm going to concentrate on the growth of commercial communications, how international phone calls, and how that opened up the world to that we know it today, and why we can make phone calls. But great big dishes. So in the beginning, when I can find the mouse. In the beginning, we had a lovely publication called Wireless World. Wonderful publication. Started way back in the early days of radio, and it's now defunct, but it was written mainly for the professional, but it was written in a very readable way that you could explain things in a non-technical way. In October 1945, an article was published called Extraterrestrial Relays by somebody called Arthur C. Clarke, who you may have heard from 2001 Space Odyssey. Well, he was a science fiction writer, and he wrote all about the idea of putting repeaters in the sky to carry international communications. Because up until that point, when people started to talk about this, if you wanted to make an international phone call, it would be on cable, and you'd have to ring up the exchange, and you'd have to say, I'd like to book an international call, I'd like to book a call to the States or Australia or wherever you wanted to go. Yeah, okay, and perhaps you'd wait 24 hours for them to come back to you. Because if there wasn't a slot available on HF radio, you were over cable. And it took a long time. Unlike today, when you can pick up the phone, you can tap in the code and the phone rings. Just like that. As if you're ringing from Newton Abbot to Torquay, you can ring Australia in the same way. How did all that come about? So this article is quite interesting, and it gives and he actually talks about what we're going to talk about here somewhere. It talks about putting the satellite at. It will be observed that one orbit with a radius of 42,000 kilometres, that's from the centre of the Earth, has a period of exactly 24 hours. A body in such an orbit, if its plane coincided with that of the Earth's equator, would revolve with the Earth and would thus be stationary above the same plot on the planet. So that was the key to what it is. So it's this, what we now call the geostationary orbit. So where is this orbit? This orbit is 35,786 kilometres above the equator, or 22,000 odd miles. The orbital speed is 1 sidereal day, which in fact is 24 hours. So it means that the speed in that orbit is the same as the rotational speed of the Earth. Which means the satellite doesn't rise or it doesn't set. To the observer on the surface of the Earth, it is completely stationary. And it's looking down from the heavens. So there's a couple of satellites there going round and round. But of course, it's got to be on the equator. Why? Well, if you think about it, if you think about the Earth spinning like that, as it spins like that, you've got two forces in force. You've got the gravity, which is pulling stuff in, but as you spin something round in that gravitational field, you've got centrifugal force taking it away from the body. You reach a point at a speed where the centrifugal force balances the gravity, and it sits there. You can do this yourself at home with a tennis ball on a bit of string, but mind you don't get dizzy. Because you go round and round and round, and hopefully you'll fall down before the dog gets it. But that was the idea, and that was mooted in Wireless World in October 45. And we're still using it today. So it's all about getting people to make phone calls. Now, we want dialing, and there's a lot of money behind this, masses and masses of money. You know, international comms people, yeah, if we can get channels up there, we can charge all sorts of people. So the whole exercise has been money driven. So it took from 1945 to 1965 until we had the first fully functional in-service geostationary satellite where people could make phone calls. But it was limited. We only had 240 voice channels, or if we weren't using it for voice, one telly. That was it. It could do either. The only way you get the capacity for being able to pick up the phone and dial instantly is you need huge capacity up there. That's what you need. So if you, as I did on many times, scan through the band looking at these satellites, 99% of the channels were just lying there empty, waiting for somebody to pick up the phone and ring. So that was 1965. By the early 80s, we had moved on to Intelsat 5. Now, Intelsat was a consortium of different companies, mainly American, different communication companies all got together, formed this consortium, and sold satellite communications to the world. This had 12,000 channels, but it could also run 2 TV channels simultaneously. This is where you used to see the BBC and the ITV reporters on here doing their bits to camera. We're just going over live to our reporter in Saudi Arabia. What the public didn't see was Jeremy Bowen picking his nose before he went on air, and some of the language used to be quite fruity. Where's me satellite? You know. By 1998, we're up to Intelsat 8, 22,000 channels, plus 3 TV, or you could actually run 112,500 simultaneous phone conversations. So masses and masses of capacity. And also by 1998, we've started to go from analog over to digital, which I'll come to in late. So that's what we've got there. And then, just to bring it right up to today, Intelsat 40, which was 2023, they all look very similar, these birds. What we're starting to see now, and have been for the last decade or so, is the comms packages on board are being tailored to the specific areas they serve. And it's all about reusing the same frequency. That's the thing. So it's becoming very tailored. Also now, you've seen the rise of fibre optic cable, undersea fibre optic cable. So a lot of the in-orbit satellites are dealing with mobile terminals. You can phone home from the back seat of a 747 using a satellite. At the last count, there's 580 satellites in geostationary orbit, including all the stuff that was put up there 40, 50 years ago. It's still there. It's still up there, space junk. What they do is they move it slightly out of orbit. That's why there's a lot of stuff up there. At some point in time, somebody's got to go up there and clear it all out. Arthur C. Clarke, in his article, actually hints about a spacecraft going out to this geostationary orbit, which is way out in space, with a crew on board, actually, you know, maintenance crews going out there to sort them out. If you go online and you look at the geostationary orbit, it's like a ring of steel around the Earth. Now, I'll come to the antenna side of it in a minute, because it's when you get up there, why do we need such big antennas? But when I'll come to that in a minute. So what does the world look like from up there? Well, that's the sort of view that you get from 22,000 miles. So looking down on the Earth, you have one number of beams. Your antennas on the satellite have got a beam. So a global beam will cover 1/3 of the Earth's surface. So anybody in that footprint will be able to communicate with anybody else in that footprint. And later on, we can see that in action. So anybody in there can communicate with anybody else. Then we've got hemispheric beams. These are antennas on the satellite designed to work from one side to the other. And it's all to do with reusing the same frequency. So if you've got somebody coming down on a global beam using right-hand circular polarization, you can also having somebody coming down on a hemispheric beam using left-hand circular polarization, and on the same frequency. And they won't interfere with each other. And then in the 1980s, we started to see the beginning of spot beams, where you're actually starting to target specific areas. So once the satellite goes up there, you've viewed that side on, that's your global beam, that's your hemi beam, and that's your spot beam. Very, very roughly, that's how the arrangements are. So to take that one stage further with the spot beams, that's what Europe looks like under a spot beam footprint today. It's a bit of a headache for the intelligence agencies, I can tell you. So looking at that map there, that effectively says anybody in the areas marked 1 can communicate with each other, anybody in 2, anybody in 3, anybody in 4, but they cannot intercommunicate or interfere with each other. So spot beams are a real headache. So it's becoming more and more like a mobile phone system. Right, frequencies. Now this is back in the 1980s, and I know today we're using a lot higher frequencies, but in the 1980s, bit of a slow rocket that one. Satellite is launched, you wouldn't believe this, I drew this slide in about 1983. Earth stations are built, and we want some links. Now, in international parlance, you always talk about go and return channels. It's duplex working. So we have a go channel and return channel. So in the 1980s, we had two bands. C-band, the uplink was 5-6 gigs, and the downlink was 3.7 to 4.2. And we also saw the emergence of KU band. And that's where all your satellite is, your domestic satellite TV sits up there. But this was entirely commercial. 500 megs of spectrum. And that was starting to carry our international comms. The return channel is exactly the same, using the same uplinks. And of course, you've got the two polarizations as well. Linear polarization on KU band, circular polarization on C band. Now, you'll see from the pictures at the beginning, the antennas are quite large. The reason is that when you put a satellite up at that height, 1 degree of movement on the Earth represents a distance of 5 to 6 miles in the geostationary orbit. So when you've got satellites close together, you need to be able to drive your antenna in fractions of a degree. So just think about the engineering involved in that. You've got a 200-ton, 90-foot dish antenna that you are turning in increments of 1/10 of a degree, or sometimes even 100th of a degree. So to the naked eye, the dish doesn't move. But when you're standing in front of an antenna panel with a spectrum analyzer looking for a satellite and it's sweeping through 1 degree, you'll see the signal appear and go. So you've got to tweak it back. So the control mechanisms for these antennas are quite sophisticated. And you're just sitting there twiddling knobs, but you've actually got to line this thing up. Once you get it locked in, there's a beacon which you can track, and then an automatic tracking system will follow the antenna, follow the satellite, because the satellite moves slightly in the orbit. It actually, as Chris said in his talk, it sits there doing a figure of 8, like that. So what sort of signals did we see on being carried? Well, the most obvious one is, as I've alluded to, is the phone call. So up until this point, when we had reliable satellite communications, the chances your international phone call would be on cable. And that was on a 3 kilohertz channel. 0 to 3 kilohertz channel. Because that's where our voice is, that's where our ears work. When we went upstairs, they gave us 4 kilohertz. 0 to 4 kilohertz. Affectionately known as the voice grade channel. Anybody who's ever worked for BT will know all about these. In that 4 kilohertz, you've got a usable frequency range of 300 to 400 hertz. So 3.1 kilohertz, that's what you can use. Anything outside of that is deemed to be interference. So all your filtering in your go channel and your return channel has to be based on that bandwidth. That's all you've got to use. So how are we going to get thousands of channels? We've got hundreds of people all want to make a phone call, and we're all talking at the same time. We all talk on the same frequency. So the first system they used was frequency division multiplexing, FDM. That's different people on different frequencies. So simple diagram here. Here we've got 3 subscribers all speaking on the same frequency. So the first thing that happens is that these channels are up converted to a higher frequency. So channel 1 will be up converted from 0 to 4 kilohertz to 60 to 64 kilohertz. Channel 2, 64 to 68. Channel 3, 68 to 72, so on and so forth. And eventually that became, when you've got 12 of these together, you've got what's called a group. A group of channels, 60 kilohertz to 108 kilohertz. That's what's known as the basic group. Not only did you see this on satellite communications, it was also the way that channels were moved around on. Do you remember when we used to have a microwave network in this country? Microwave towers with dishes on? That was how phone calls were moved around the country. So there's a hierarchy. So we've got one basic group, which is 48 kilohertz wide. 5 of those stuck together is called a supergroup. 10 supergroups together is a master group, and 6 master groups is a jumbo group. Now, I've never seen a master group or a jumbo group on satellite. There's not enough room. But definitely I've seen 4 or 5 supergroups on one carrier. Remember, this is AM single sideband. They're all AM single sideband. They're not all upper sideband, some are lower sideband as well. But there was you could talk for hours just on this multiplexing system. So you might get one country says, okay, I need 60 voice channels to cover my, so he'll get 60 channels, 240 kilohertz. You could actually demodulate this stuff with an HF receiver. When they had HF receivers that went down to 30 kilohertz, you could actually tune through these, just switch upper or lower sideband. When you've got your multiplex together, when you've got your block of channels together, it was then transmitted up to the satellite as FM. So you've got all those AM channels. So you've got this great big AM signal, AM single sideband signal, whacks it up to the channel as FM. Because FM was a more efficient way of transmitting it. But that was FDM, and the same thing happens at the other end. So you'd have lots of groups coming in and up, and the whole thing was turned around at the other end. We live in a digital world now. Do we still have any FDM around? Probably not on satellite. But there's one not very far from here. Our very own analog FM broadcast. Radio 1, Radio 2 is actually AM SSB. It's a multiplex. Even though you're tuning it in FM, you've got a multiplex of 0 to 15 kilohertz AM, which is your mono signal, and then the 2 left and right channels there. Your VHF receiver splits that out. When you are in front of your stereo and you switch from stereo to mono, you're basically switching from that signal to that signal. And for all you buffs who bought massive hi-fis back in the 70s and 80s thinking, oh, this amplifier is really good, it goes up to 25 kilohertz. Look at that, that's wonderful, that's got massive bandwidth. You ain't going to get more than 15 kilohertz from BBC Radio 3. That is the maximum amount of audio you're going to get can't remember 15 kilohertz. I can't even if I remember hear that high. But that is the if you could look at it now. Recently, the RSP company, to make the little RSP Duo and RSP Play, they brought out a new bit of software called SDR Connect. And if you look on there, if you tune in a local radio station, you've got a display that you can look at. You can actually look at the multiplex display, and you can see the pilot tone. That's what locks your stereo unit up, and you can see the little two-tone signal there at 57 kilohertz, which is carrying the RDS signal. And you can actually see it on the screen. Quite a good bit of software, but I think it's still in development. Anybody used SDR Connect? Yeah, 1, 2, yeah. It's gone. So that's an example of analog multiplexing. So I talked about what we're going to carry in this voice grade channel. First thing is obviously speech. So that fits nicely in there. Everybody talks there. So this is what, in the 1980s, this is what would have happened when you want to ring Great Aunt Matilda in Australia. So you pick up the phone. That's you punching the numbers out on your telephone using a system called dual tone multi-frequency, DTMF. We've all heard of it. Old-fashioned dial phones used to use pulse dialing, and that was converted into DTMF at the exchange. So you picked it up, all right, okay, you go straight through to your area exchange. The area exchange, that's the local one down the road. All they're interested in is that 00. As soon as they see that 00, oh, right, over to the international exchange. The rest of the number then is not read. It just gets transmitted down the line. What happens to it is it gets converted into another tone dialing system called signalling system number 5, all laid down by our friends in Geneva, the ITU. You come across that before? Signalling system number 5? Right. But notice what's happened. What's the international exchange done? Oh, he knows a country code. No need to do that. It just says, right, I want a line to, in this case, Hong Kong. Don't need to, there's a line to Hong Kong. Where's that line going? Well, it just so happens, this time, it's going via satellite. So, that number is sent over that line. And the only number that's sent down there is the area code in Hong Kong and the subscriber's number. No need to send that. And then at the other end, right, Hong Kong Earth Station 027 goes through their international exchange, selects the line to the area, and rings the phone. Isn't it? Wonderful. Hello, Chinese takeaway, what do you want? Right, and that's how it works in the 70s, 80s, and then slowly but surely we start to go digital. Now, it used a system called in-band signaling. In other words, this number, these tones were transmitted on the channel that you were going to use. And as that line went out, what would happen with this signalling system number 5, it would go out, seize the line, and there would be a line was seized and you get an immediate response. Now I could stand up here and talk all day about signalling system number 5 because it was a very, very good system in its time, but you wouldn't use it today. Now, to the manager at Intelsat, that's a waste of time. Why are we sending all these digits out? You know, we could be using these voice channels and getting revenue for them. So what they did was they got rid of signalling system number 5 over a period of time and replaced it with signalling system number 6. What signalling system number 6 did was say, right, all this data, we'll take that out of that and we'll squirt that down a digital line with an assignment channel on it. And then eventually, signalling system number 6 was replaced by signalling system number 7, which is what we use today, which is what drives your mobile phone network, where you can actually, that's why as soon as signalling system 7 came in, that's where you got the fact that you can have the number come up on your phone, who's calling me. Because it not only sends who I want, it says who you are as well. And that's why you get that. Right. Of course, the other thing we got is data. We've got lots of data, but we've only got 3.1 kilohertz. Not a lot of bandwidth there, guys. How did we used to do it on HF? Well, we used to send international telegrams via teleprinter on HF. You could go into a post office in a far-flung place in the Empire and say, I want a cable home. And you write out your telegram, off it would go to the local cable and wireless office. Somebody would sit there in front of a teleprinter, tap it up, and off it would go down over a satellite. But on a satellite, it would be a simple frequency shift key data signal, RTTY. But it wouldn't be one like what we use. They'd be crammed together inside a small channel. So when satellites came along, they thought, well, there's a perfectly good system here. Let's just take it off HF and put it upstairs, which is what they did. It's horrible, isn't it? So this was another one of our friends in Geneva's recommendation. This was a 24-tone system. Each tone, from 480 up to 3,100 hertz, is 120 hertz apart. And each tone would shift from mark and space 60 hertz. That would carry your international messaging, your telegrams, and it also carried the telex network. Now, do you remember every time you looked at somebody's company's advert, it was, you see websites now, telex, and they would give a funny little letter which would be the telex answer back. Now, the telex was basically a teleprinter, RTTY with a dial. So you dialed the telex number, the telex machine at the other end answered, and the two secretaries could then have a chat and say, oh, I've got some traffic for you. It was the digital equivalent of the phone call. That's all it was. So you could send a telex. So this would be in one sideband. Now on HF, you used to have 18 of these in each sideband, 18 tones in each sideband. and it was called independent sideband. So you'd find one of these on HF, and all they did was extract that, stick a few more tones on it, and stick it upstairs. But obviously, you've only got 24 data channels. Frequency multiplexed together, and slowly but surely, somebody got their heads together and think, actually, if we put some more channels inside the 4 kilohertz channel, we get some more money. So there were, and I'm not going to dwell on these because I could spend hours talking about these. So there were a number of different modems appeared. A modem is an analog to digital system, digital to analog. We all remember the days of dial-up modems on the internet, don't we? Yeah, right. Well, the V26 modem, this is just the ITU number. It was 4 phase shift keyed at 1200 bauds. And that carried a system called R101, recommendation R101. But because it used time division multiplexing as opposed to frequency division multiplexing, you could actually squeeze 46 teleprinters signals inside that 4 kilohertz channel. If anybody wants to know why I've put 2,400 bits per second up there, we could talk about bits and bauds outside this lecture. But that was the speed of the data, not the speed of the signal. That was the telegraphic speed. Then there was V27, which was 8 phase, 1600 baud, data rates up to 4,800 bits per second, and that carried data and fax. So people could have their own data network, their own system. In the 1980s, computers started talking to each other. And of course, what we got was facsimile machines, digital fax machines that could operate on a phone line. And this baby, I love this one, V29. 16, ooh, quam, what's that when it's at home? Well, not only are you changing the phase of the signal, you're changing the amplitude of the signal as well, which gives you 16 states. Run that at 2,400 bauds, and you end up with a data throughput of 9.6 kilobits. And it starts to carry something called X.25, packet switching. Anybody remember AX25, amateur packet? Based on that, X25. And again, if you want to talk about the OSI 7-layer model and how the internet's put together, that's, but yes, the internet was starting to be carried over satellite. Very, very basic internet at that time, of course. But X25 was a packet switching system. And the idea of packet switching is that I'm station A, I want to talk to Lynn, who's station B, but I haven't got a direct path to him, but I have got a link through Bill at the back, who's station C, so I go that way. And you imagine everybody all linked together. So it doesn't matter what link you go on. And that was carrying data to start with, then eventually started to carry voice. Voice over IP, have you heard of that? Yeah, you started to see that. And that's why you could find a link running from, say, Egypt to Europe, Egypt into Europe, carrying a link between North America and South America. And what? Yeah. It's because it was networked. And then things started to get really high-tech then. We had data rates going up, 14.4 kilobits. and then this beast here, baud rate started to increase. Something called trellis code modulation, which is extremely complicated. You need a pretty good head for maths to really understand it. But when I used to teach it, I used to say to guys, look, this is basically a forward error correction system on the modulation rather than the data. That's all it is. It means that when I change my signal from a phase shift of that amount and an amplitude level of that amount, the guy who's receiving it is saying, is that right? If not, I don't want it. If it is, I'll take it. And what it should be. So that was about the limits we went to. Now, what did all this sound like? Well, I was grovelling around on the internet the other day and I came across this. This is a recording which you may have heard before. A facsimile machine. That's what a V29 modem sounds like. Just a noise. The little warble, the FSK is a handshake. But that's what a modem sounds like. All within the 3.4 kilohertz or 3.1 kilohertz that we've been allowed. Why does it sound like just a straight white noise? Well, in these modems, they had what's called a randomizer to scramble everything. But it wasn't scrambled for reasons of keeping things secret. It was scrambling the data so that all the patterns that you get in data were just basically randomized. It was pseudo-random. And that had the effect of spreading the energy nicely across the allocated bandwidth. It was all to do with keeping the levels nice. If you had a badly adjusted modem, you get something like that up there. But so that's what we were. Oh. And then in the late 1980s, somebody thought, actually, we could make a lot more money if we got people doing digital. So how do we digitize all these voice grade channels? So back to basics. That's what we've got. We've got lots of analog 4 kilohertz channels. I'm sure you all remember that from your days of Mr. Nyquist in 1928, and again proven in 1949, came up with the sampling theorem that if you want to capture all the information inside that analog channel, the minimal frequency, you take samples of it, you've got to have twice the highest frequency. And this is the fundamental thing that drives our CD players, digital radio, all of that. Everything has to be sampled. So, well, that's fairly simple, isn't it? I need to take 8,000 samples per second of my telephone channel in order to get an accurate copy. So there it is. I'm just taking snapshots of it, of the signal. And what I end up with is something like that. And that's what I end up with, is pulse amplitude modulation. Just taking snapshots of my analog signal, and I end up with that. Not particularly nice signal. This is what happens with your amateur radio DMR. This is what's happening inside your little handheld. And then we start doing something really clever with it called quantization. So each sample that we take is allocated a number. We give it a number. So, and we use binary. So I'm using just 3 binary digits here. So we say 4 samples, 0, 1, 0, 1, 0, 0, 1, 1. Every level is given a number. So, for example, on that sine wave there, if I've got 8 levels, I can use 3 bits for each level. But you can see from the number of samples that I'm going to end up with a pretty ropey signal, because there's quite a long time between each sample. I've missed quite a bit. If I go up to 4 bits, which is 15 levels, I get a much better quality of signal because I'm taking more samples. So that's the basic principles of digitization. So each of those numbers, 0 and 1, we'll say are given a signal level, 0 and 5 volts, and you transmit the whole thing as a serial binary stream. So back to our 3-digit example, when I get a value there, this one here, 100, right, okay, 100, on, off, off. And what I've created there is pulse code modulation. So sine wave input, sample it, quantize it, and you get PCM. Now, back to our telephone channel. To get the maximum input, what we do, and you could have any number, but the number that was settled on was 256 levels. So we've got 256 binary chunks, 8 bits long. So if I sample up 8 kilohertz, 8,000 times 8 bits equals 64 kilobits. And that's where the 64 kilobit channel came from. That's the fundamental building block of all international digital comms. How do we transmit it? Well, we don't use FDM because we've got data now. We use time division, and one of the systems, and there are a number out there, the one that was used in Europe is the PCM30 system, known as the E1, and it's put into a frame. So you start off with a synchronization 8-bit sync at the beginning, and then channels 1 to 15. So the first frame that you send, 256 bits long, that would be a synchronization. Then that would be the first binary word from channel 1, first binary word from channel 2, so on up to channel 15. That's for signaling and admin. Then another 15 channels there, all the way up to 31. And that would run at 2 megabits when you added all that up. So that's how you can transmit 30 64 kilobit voice channels. Wouldn't you know, there's a hierarchy. So if I take 4 of those and strap them together, I get an E2, and 4 of those strapped together, I get an E4, and so on and so forth. Right up to the E5. Now, it might interest you to know that 1E1 is 30 telephone channels, right up to the E5, which is 7,680 channels. But it is running at 500 megabits, which is quite a high speed. It's not going to fit in a 4 kilohertz voice channel, so we've got to go over to a whole new method of transmitting this stuff up to the satellite. And we use something called a satellite modem, which I know is very dear to Chris's heart. So basically, I've got my multiplexer with my PCM stream, however many channels I want. I feed that into a satellite modem, which will chuck out 70 megs. My stream, it's old. Yeah, it's a long time since I've done this. Yeah, I know. Yeah.
Don't use 70 megs anymore.
Yeah.
Even 140.
And then you upconvert it, basically, onto a whatever uplink frequency you're using, up to there. And it was transmitted using phase shift keyed. That is basically how they digitized international comms. Then they started to get really clever. And I won't go into this in too much detail, but okay, we've got a voice, 8-bit words being sampled. And somebody said, hang on a minute, 8 bits, that's quite wasteful. Can't we get it? Look, you might get the first sample and it's level number 1. The second sample, so that only gone up to level 3. Well, all we need to do is send the difference between level 1 and level 3. That's all. So actually, when they put their heads together and worked it out, you could get away with sending all the bits, all the necessary information, only by sending the differences between each sample. Differential pulse code modulation. So suddenly, your 30 channels can become 60 channels because they only use 4 bits to send the differences. They only need 4 binary digits to actually say the difference between 1 and 2. Yeah. Then, the next thing, right, okay, we go for differential pulse code modulation. And then somebody said, well, let's think about a telephone call. I'm phoning Aunt Matilda in Australia, but when Aunt Matilda's talking to me, I'm not saying bugger all. Well, somebody else can use my channel. Gone. Aunt Matilda stops talking, I take a deep breath. Oh, you need a channel again. So, that gave birth to a system called Digital Circuit Multiplication Equipment, DCME. And there were about 3 or 4 companies in the world that actually grasped this by the nettle, one of whom was an Israeli company, wouldn't you know, and started to sell this to the world. And you could literally put your 5 E1s into one of these boxes and get one out. So for 150 channels in, you had one digital stream out, the size of the original one. And that's when, DCME took off big time. And that's when I hung the headphones up then. Right. I'm nearly there, guys. Esailsat. The Qatari satellite company. Oh, who are they? Right. They've got a lot of money. They launched their second satellite, SHAIL-2, on the 15th of November 2018. to serve telephone, television, data networks for around the Qatar region. SHALE-2 also provides the first radio amateur satellite in geostationary orbit. We call it, well, AMSAT call it QO100. And on there, we've got a narrowband transponder and an 8 meg wideband transponder, which we can use for data. Now, the narrowband one carries all our usual amateur radio stuff. The wideband transponder carries digital television. 2.4 gigs up and 10.5 gigs down. So that's what that's the sort of things that you've got. You've got two beacons, a CW beacon top and bottom, which are the same, and you've got a PSK beacon in the middle. CW, narrowband digital modes, SSB, and there's an area up the end for contests, although I haven't heard many contests on there. What you're not allowed to use on there is DMR because of the bandwidth. You're only allowed 2.7 kilohertz bandwidth to use. Where is it? It is situated at 25.9 degrees east, just above Africa. That's it there. So that covers the UK. We have, where the Astra is, yeah. I think the longest contact has been from somebody in Brazil to somebody in Singapore. But obviously, if you were situated there, your antenna would be looking straight up. So up here in the UK, I'm probably about 20 odd degrees elevation. 26 degrees, is it? All right. I've not used it, but it's something I wouldn't mind having a crack at. But that gives us coverage, so you can work DX on there. You'd have to move the satellite, and as the Qataris are paying for it, you know, I mean, it's free to use, provided you.
Don't worry, Trump's Riviera's covered.
Yeah. So basically, it's a 2-meter transmitter through an up converter into your dish, 2.4 gigs up. Yeah, and then down, and then down. Now you can build your own kit, but there is also off-the-shelf, ready-to-go earth station made by a company in Portugal called DX Patrol. It's 990 euros, and it sits on the shelf. And all you need to supply is the dish, but all the bits are there and the cables. If you watch the latest edition of TX Factor, you'll see Bob McCready, who set one up and has done it. Now, to listen to it, I said 70 SEMS, or you can use a WebSDR. So now I'm going live now, so this might not work. This is the QO100 WebSDR. Oh, that's live on the. Right. I don't know, what am I doing wrong? No, I want to leave it on here. I was going to get the beacon up. I want to leave it on the web. No, leave it on the web. Leave it on yeah. That's it. Can I see it on there as well? Ah, that's it. There we are. So, 748. That's the mid-band beacon, 8-phase shift key signal. There's also 2 other little beacons up there. If I can just find the, that's the mid-band beacon. There's an upper and lower beacon. 489. Yeah, sorry about the noise, but it 10, 4, 8, 9, 12 words a minute. That should be QRA DK0SB. So these beacons are little FSK beacons. HI, DE, QO100. The rubbish Morse program. There is. You have to. Trouble is, all these Morse reading programs, you have to get them set Anyway,
We need a Derek.
Who's Derek?
not at 12 words a minute. That's,
A quarter of a Derek.
right. Okay, chaps, that's the end of the talk. Anybody got any questions? Thank you very much.
If we got so much digital compression out now, then Don, I've still got to dial an area code when you want to play with my mobile phone.
You've got to dial an area code because what they decided to do was say you've got to, when you've got to go digital voice, it's like an address.
Yeah, so I mean, so dialing across access hills, you don't want 3 lines.
Yeah, it's the same here in Torquay. If I don't need to dial 01803 on my old analog phone. If I switched over to digital voice and went down the fibre optic line, they want me to put the code in, area code, same as on mobile phones.
That's what I'm saying.
Yeah.
There's so much,
They don't make it less because they don't think people actually type in numbers now. They put the phone in the memory and it's just like press a button, memory. Fred, go.